Hey everyone, welcome to today's Explainer. Even if you're already pretty familiar with that whole alphabet soup of network protocols, we're talking BLE, Wi-Fi, LoRa, Zigbee, trying to figure out how they actually interplay at a fundamental physics and architectural level, well, that is a fascinating challenge. Today, we're decoding the architecture of IoT networks using some really fantastic source material. We're going to break down how these invisible webs of communication actually function, how they evolved over time, and the strict laws of physics that literally govern them. It's an incredible journey, going from early military research all the way to the billions of connected devices we rely on today. And we've got a highly visual slide deck to make it all crystal clear for you. Let's get into it. Okay, let's look at our roadmap for today. First, we'll cover the sensor network origins, then building the mesh topology. Third is the connectivity trade-off, followed by understanding Wi-Fi, BLE, and 802.15.4, and finally, navigating the protocol stack. So, starting right off with Section 1, the sensor network origins. It's incredibly easy to think of the Internet of Things as this purely modern phenomenon, right? Like something born totally in the era of smartphones and smart homes. But to truly understand these networks, we actually have to look back much farther to lay a solid historical foundation. Because modern IoT was heavily pioneered by US military programs and academic institutions long, long before it became a household term. Just look at the very beginning here, all the way back in 1978 with the DARPA Distributed Sensor Nets workshop. That workshop directly led to the DSN program in the early 1980s. Fast forward just a bit, and by the mid-1990s, you had academic powerhouses like UCLA partnering up with the Rockwell Science Center to develop WINS, or Wireless Integrated Network Sensors. And right on its heels, in 1996, came the Low Power Wireless Integrated Microsensor, or LPWIM. The core challenge they were trying to solve all those decades ago, it's the exact same one we face today. How in the world do you get tiny, low-power devices to reliably talk to each other? Which brings us to Section 2, building the mesh topology. This really addresses the crucial physical architecture and answers a huge burning question. How do these tiny battery-operated sensors actually transmit data over significant distances without just dying in a matter of hours? To answer that, take a look at this multi-hop mesh network diagram. Notice that blue dot? That's your gateway node. And all those dark circles represent individual sensor nodes connected by this intricate web of paths. Think of it kind of like a classic bucket brigade fighting a fire. Instead of every single person running all the way from the water source to the fire, which obviously would be exhausting and terribly inefficient, each node simply passes the information along to its neighbor until it finally reaches the gateway node. The sensors themselves are essentially acting as forwarders for the other nodes. So the crucial point here is exactly what this comparison breaks down. In a single hop setup, every single node tries to talk directly to the gateway. For the distant nodes, doing that requires a massive, battery-draining shout, which heavily limits your network coverage. But when you move to the multi-hop or mesh topology, absolutely everything changes. Because the sensors are acting as forwarders, you dramatically reduce the overall energy consumption and vastly increase your coverage area. The only catch here, it requires a routing protocol to manage all that traffic efficiently. All right, moving on to Section 3, the connectivity trade-off. Now, this brings us to the core tension of our entire explainer today. When you're dealing with wireless communication, you are constantly battling the strict, unyielding laws of physics. There is this absolute trade-off where you simply cannot have long-range communication, incredibly high speeds, and ultra-low power consumption all at the exact same time. You literally have to pick your battles. Notice how this scatter plot visualizes those exact trade-offs. The y-axis on the left represents power consumption, going from a tiny little 1 milliwatt at the bottom all the way up to over 1 watt at the top. The x-axis along the bottom represents distance, stretching from 10 meters on the left to a massive 5 kilometers on the right. And finally, those blue concentric rings, they represent the data rate. Basically, the bigger the rings, the more data is being pushed through. This scatter plot is essentially the ultimate cheat sheet for understanding exactly why certain protocols are used for specific jobs. Let's go ahead and demystify the clusters from that chart by looking at the rule of 3, power, range, and speed. Down in the bottom left, we've got short range and low power protocols, things like NFC, BLE, and 802.15.4. These guys operate around 10 to 100 meters, using a minuscule 10 to 30 milliwatts. Now, move up that y-axis and you hit medium range and high power. That is your standard 802.11 Wi-Fi, pulling around 1 watt. Look over to the far right and you find long range and low power protocols, like LoRa, which can reach up to 5 kilometers but sip just 10 milliwatts of power. And finally, up at the top right, long range and high power. That's LTE, giving you those massive data rates across huge distances, but as you'd guess, at a tremendous energy cost. Up next is Section 4, Understanding Wi-Fi, BLE, and 802.15.4. Let's zoom in on three of the most heavily utilized standards detailed in our source material and really compare exactly where and why they're used based on those physics trade-offs we literally just talked about. First up, we have IEEE 802.15.4. Now, this is explicitly designed for wireless sensor networks. It's low power, has a max range of 100 meters, and a low data rate of 250 kilobits per second. It's incredibly widespread in academic solutions, and it actually serves as the very foundation for commercial protocols like Zigbee and 6LoadWAN. Next, compare that directly to IEEE 802.11, or as we all know it, Wi-Fi. This one operates at medium power consumption, so it's strictly for nodes without severe energy constraints, which is why it completely dominates commercial applications. Finally, there's Bluetooth Low Energy, or BLE. It brings us back down to low power consumption, but its key differentiator is that it's designed specifically for nodes to communicate directly with mobile devices. And that brings us to our final part, Section 5, Navigating the Protocol Stack. So now that we have a really solid grasp on the physical wireless standards, let's look at how we built a fully functional network from the ground up using protocol stacks. This is where we transition from the physical hardware out in the field over to the software layers that actually organize and make sense of all that data. Step one is the addressing scheme. Whether it's the older IPv4 or the vast IPv6, every single node needs an identity. Step two is the data transmission layer. This is where those physical protocols we just learned about, like 802.15.4, Wi-Fi, BLE, LoRa, or even 5G, actually move the data at their respective transfer rates, whether that's in kilobits, megabits, or gigabits per second. Finally, step three is the application layer. This utilizes protocols like CoAP, MQTT, or HTTP to take that raw transmitted data and turn it into an actionable process on a server or an app. It is just a beautifully logical stack when you break it down. So, as we wrap up today's explainer, I really want to leave you with a question to ponder. We've seen how brilliantly engineers use mesh topologies and these varied protocol stacks to navigate the very strict boundaries of physics. But given those unyielding trade-offs between power, range, and speed, what is the ultimate limit of sensor networks as billions and billions of more devices come online in the near future? Will a massive breakthrough in battery tech just rewrite the rules entirely, or will edge computing completely change the game? Keep that in mind the next time you pair a smart device. Thanks so much for joining me today, and keep learning.